All right, that should be started. This window. Where's the thing at?
Should have been right over here. I've been had by myself.
And here it is. And there's something loose just floating around in there. Oh, that's great. Alright. Let's see. My desk might be a mess, but it has everything in there somewhere. Which is good enough. Is this audible? All right. Let me check and make sure recording's going. It says it's going. Good enough for me. It's almost like, is the question, is this audible? Is the thing I'm asking is if it's audible, but, you know, whatever. So I haven't slept since like 12 hours, just about, so y'all gonna get delirious, rambling, but with notes to prepare it. So, let me make sure I'm getting the right synopsis here because I've done this like 5 different times. Rudimentary transformational functional theories derived in the internal harmony with a context-rich functional whatnots. All right. So now that I've got that set up, so the basic synopsis of this thing is hopefully accurate. Which I'm going to just, this thing. Masterful use of MS Paint. Which, you know, whatever those words are, abstracted systems of music and development of associated theories of harmony, it's pretty much meaningless without some prerequisite definitions going on here. So, going over just some basic definitions of what some symbols are going to be. Whenever I say generic musical system, it's going to consist of 3 key parts, which is going to be your W, your R, and D. W here is basically your collection of your basic syntactic objects. You know, your basic atomic musical objects, the chords, if you will. Which, you know, is not completely inaccurate. R here is where all the semantic classes are, where you're, if W is your space of what's written, what it is. R is the space of how it acts. Reading the notes I have written down on my side, the space of relevant semantic objects given meaning to objects of W. You know, this nasty collection of semioclasses. But in essence, this R is just a collection of functions, more or less. And it's not only a collection of objects, but also has some arrows between them. And D here is where the real magic happens. And this is how everything happens, because D, in essence, encodes the entirety of the context-free functional behavior of your system, along with the structure of the arrows on R, because this is just a little function from W to R, where you identify any chord W with the associated semioclass D of W. Which, it's like saying, oh, that's not a specific spelling of a C chord, that is C chord in brackets. It's a sort of a generic idealized functional shape. It's less of more of a function as in dominant, subdominant, predominant, what was the other ones? Mediant. It's less of that, and it's more of a generic idealized like pre-function of sorts, saying this is a chord which looks like this, and it relates to whatever other chords through arrows. So you have your A, not like an A chord, but generic variable. You got a B, a C, and with your arrows between them in whatever fashions they might take. But see, this is where we run into a slight issue. And there's two paths I see right now, which both you could argue as being correct, up to a choice of a convention. So R here has its arrows, right? But here's the kicker. Are all arrows important? Or are there unimportant arrows between all objects? And the distinction between the two, it should have non-trivial consequences in the formal workings, but in the actual conclusions you draw from it, it should be roughly equivalent. And any inequivalent consequences derived from it with musical meaning and not just mere pushing a symbol should be attributed to a mild difference in interpretation between a functional or transformational basis. Or something like that. Might not be exactly the right terms for it, but should get the idea across. So, the convention I like is every single object in W, let's say you have W and V, lowercase. For any two objects there, you can pick out an associated transformation here, which relates to a transformation from W to V. But that is not necessarily an important one. Rather than speaking about, oh, you can get from A to B, it's more important to think about, can you get from A to B in what would be deemed best practices, quote unquote, in whatever system you're dealing with. And we're just going to say that our special privileged class of transformations that we care about are admissible. They don't have any special properties or anything. We just pick them out randomly. Or not randomly, but arbitrarily. If you didn't write down notes for that, it's fine, because that's not the important bits. That's just necessary if you're going to rewatch the archive video and try to understand what's going on formally. Merry Christmas. Also relevant is this nasty little thing. Looks like a G, but it's actually a weird font of S. And this SW here is probably the nastiest thing you'll ever see in this context. This is absolutely not a set. It's more like a proper class. And you just take everything of shape delta. So delta here is like a graph or category, something of that fashion. Which there is an upper limit, but I do not know exactly where that upper limit should be. So this is satisfactorily large. So for every delta here, which satisfies whatever conditions that it's not some horribly obscene thing, for every delta, you take every little composition which maps points in W over delta. So, delta could be like a triangle or something. A, B, C here. It could be like a triangle here. And you could map these to, say, the note A4, C4, E4, and you get yourself a minor chord. So that's a single delta, which can map to any triad with a specific ordering to the numbers. But you could do that for any delta that's not super awful. So with that out of the way, we're going to ignore most of the formal underlying things here because that's not the point. You can do anything you want with all the symbols and all the models you want, but if it doesn't give you a musically meaningful thing, it's not music theory, it's just self-masturbatory mathematics. So now you have to justify that whatever you're doing actually makes sense in a musical context, which is the actually difficult bit, because you could slap any numbers together and call it a model. The important bit is if it actually models what you want it to. So, ignoring all the formal underlying mathematics going on here, if we have W, R, D, with taking the convention that there are transformations that are not important, or transformation classes technically, but taking that convention, let's collect all three of these into some single fancy H, because I'm not writing down all three of those every time. Taking all three of those down, you can arrive at a few immediate conclusions just based on our definitions here. D works on single points from W to R. So rather than actually working on to analyze a musical composition, you're kind of just analyzing it at any given isolated point in time, which should very obviously not be sufficient, as is, to develop a full theory of harmony, yes? And it's not to say that there is no contextual information, actually, because there is the possibility of some information like this is in the key of C minor or whatever encoded into what's allowed as transformations in R. And instead of working on single notes, you're working on chords and whatnot. Literal chords. But that's... even if you have that bit of context, it doesn't tell you how each individual chord relates, especially because not every C minor chord is the same. Even if they are the same C minor chord, they're not acting in the same fashion. So, if we take our nasty, horrible SW with the horrible fractal font, now we have things that actually give us some minimal contextual information. Because now we have a structure to it. From delta to R. Delta here has arrows. R here has arrows of its own. And those arrows might not agree in any way, shape, or form with each other. But you have both of them. And if you couple that with some of the admissibility functions, it's possible to actually get something from it. So, you have, for any little arrow you have in delta, like this arrow here, you should have an associated arrow in here. And it's either going to be in the same direction or a different direction, but not only do we have an arrow, we also have not only have an arrow parity of in the same direction or not, we also have a question of is it admissible? And this admissibility condition is important in that it's roughly the same as a very vague, generalized sense of resolution. You know, in the same sense as going from a dominant function to the tonic is of resolution, even if you've got some crazy extensions like a sharp 11 or something, because it's functionally resolvent. Touch this thing. So an admissible, why is that still yellow? But So an admissible arrow from point A to point B could be taken as a resolution in that direction. So if we have that transfer over from delta to R in the same direction, you could consider that an admissible movement. An admissible point in omega, the composition, from delta to W, so that's an admissible point right here inside this little thing here, because, you know, it's not going to point out the same points here because this is more of an X and Y, which then get mapped to A and B. Because all delta is a structural idea of where are the pieces of your music and how do they relate to each other. Not necessarily in a linear fashion, but perhaps in some horrific branching fashion even. Like, I forget who the guy is. It's the guy who does like the two pianos playing a similar thing, phasing into each other. If someone knows it, just throw it down in the lecture chat. I can't remember this guy's name, something minimalist. That's less linear, and there's kind of a vertical relation between the two, acting in parallel. Yeah, Philip Glass, that weirdo. That was crazy. But see, all delta does is tell you where are things happening. It doesn't tell you anything about what's happening, because everything that's what's happening is this omega here. And omega, the elements of the SW, you could just call it a composition in the system. I mean, no matter what term you call it, it gets the point across. So long as it makes sense, I guess. So, if your thing goes in the same direction, that's good, right? Because it means you're going downward in intention. Downward in quotes. Because, you know, it's not like this mess of resolutions that actually linear. If you drew it out with like stuff on the top, drew stuff on the top, the bottom and stuff, you'd end up with like weird branching lattices that may or may not have top and bottom elements, like so. So that's a good looking example. Normal ones would just be bad. Horrifying. So, it's not going... I'm just going to say downward motion tension, because that's what it feels like anyway. So that's when it's in the same direction and it's admissible. What if you change the direction? Is this still good? What do you think? Because, after all, it's still an admissible arrow, right? It's still something the system says should be allowed, just it's in the opposite direction. So, these pesky little fellows are contraadmissible points, or contraadmissible transformations. So like at a transformation T in delta, it's contraadmissible. You know, you can't exactly say at point X, because there might be some other point Z which it also maps to, and then goes to Y later, in some kind of demented triangle. So you can't just say, oh, it's contraadmissible at point X. It has to be at the transformation between X and Y. which may or may not be unique. So a contradmissible, if an admissible one is a resolution, and a contradmissible one is pretty much the opposite, stands to reason this is going to be more tense. You go upstream for tension, downstream for I don't know, resolution. I don't have a better. It's a knee there. Makes it. So you want. I mean, you could just as easily change the direction of the arrows, whatever. It's just a not. It's a meaningless choice of convention for the arrows to be in this direction. But as long as we're completely internally consistent with it, it doesn't matter. And this particular convention here, if you do some stuff with some partially ordered sets, turn them into categorical things, flip the arrows around, you can actually get something that works rather nicely for actual, more concrete versions of this. Which are, they're still nightmares because whatever expressions you get are going to be nasty, but... So we can say that any given transformation here is going to be contra or not so contra admissible, right? So what if every transformation in delta here is contra admissible? Then you could say the entire thing of delta is, well, you wouldn't actually want to say that every arrow is admissible exclusive or contra-admissible. You'd want to say it's more of an inclusive, or that everyone is either in the same direction or against the same direction, mapping to admissible ones. So you would call it more of a semi-admissible. Which, since those are going up and down in the tensions and releases, that would roughly be equivalent to the composition following our system's best practices. You know, it's doing what the system was designed to look for. So the semi-admissibility, it doesn't do a whole lot mathematically, but if it does not satisfy, but if it satisfies that condition, not doesn't, if it does satisfy the condition, and it's and we say that if we have delta being small in an informal sense, and furthermore, if we have delta be connected, you could consider a small connected delta thing, which is to say you're not going to have random islands unrelated to each other in the structure, you know, like up here's some chord, here's some chord, and they're not connected. Why would you have that at all? Unless you're doing like some weird symphonic movements that have no relation to each other, in which case you're a bad composer, but hey, that's outside the scope of this. So if it's small and you have the semi-admissibility condition, you could say it's let's go with local composition. These local things, your basic building blocks. Everything runs off these. And you know why they run off it? It's because they're nice. Not only are they small, quote unquote, but everything's important to everything else. You're not going to have some random chord which is unrelated to what the meaning of this other chord is. Right? The whole point of the locality condition and the smallness, quote unquote, is that no matter where the points are here, they relate to each other in some fashion, no matter how many other middlemen they have to go through. So, skipping any actual formal definitions, a local composition is nothing more than a small snippet where everything is important. If you can split your whatever big thing you want to look at into these small little snippets, you stitch them together, it makes things look a lot nicer. It doesn't necessarily get you the whole picture in doing so, because you're gonna miss some motivic recurrence going on there, unless you start nesting things. So let's say you have your little local bit here, local bit here, local bit here. You know something you could do? The local bits are now basic things. Uh-oh, you've gone another layer up. And instead of transformations, you'd have transformations which act on every point of that local thing. So you'd have triangles going to things which are related to triangles, something with a basic, vaguely triangular shape, or maybe the other way around. They're gonna be related in some way, shape, or form, and furthermore, the relationships between them, because we care about semiadmissibility. You're going to have when you're on the first scale, everything's admissible, contraadmissible are unimportant. Now you're going to have semi-admissible singular transformations here, because you're going to have more than one transformation between a bunch of points and another bunch of points. But if you go through all this nesting here, you go up several layers with just this whole thing, you end up with a roughly transformational theory of it. Yeah. Should end up with that, because, if you have some arrow here, you want it with these arrows here being the admissibility arrows. You'd want it to map to something else that is similarly shaped. The arrows can change direction, but if you have some extra point here, you're not going to have it change to something else. It's going to be the same basic shape, even if the arrow directions are going to be changed. And no, do not tell me you can just rotate the thing and flip the thing around. I'm assuming everything's in the same spot as it was. It's a parallelogram, not a triangle with a stick on it. Anyway, so you can go through however other many layers you want to go with the transformational stuff. But see, why would you want to do transformational stuff when you can do functional stuff? Because some of that transformational stuff is kind of sus. So, let's say you want to do something functional. Now you're in a lot more trouble, because your admissibility things are roughly, this kinda, yeah, you can kind of go from A to B, and it's a resolution. It's the direction that's going downward in energy, so to speak, or the other way around, going upward. But surprise, surprise, functions are not decided entirely by the chord and its successive chord. You know, just having D, you know, a D major to a G minor. What's the function going on here? If you said it's a VI of some sort, you might be right. But it's not necessarily always going to be that, because you could have something weird if you, yeah, it's IV, not VI. You could have something like that, which are pretty similar, but whoops, they're different because they have a different tonal center. So you can't just look at an arrow in isolation. You've got to look at more of a bigger picture. But surprisingly, that's kind of difficult, because between our triangles or whatever other accursed shape, we no longer have admissible or inadmissible or contraadmissible. Now we have semi-admissible. Well, you know, you could technically have something that's fully admissible or contraadmissible, I suppose, but you know, those aren't going to be the majority. So you just have a semi-admissible in all the arrow directions, scrambled. So how do you get a meaningful sense of function from that? You can't even say the direction of arrow here matters anymore. You know, is it this way? Is it this way? Is it even important at that point? You know, it's important in our reasoning where we're justifying that it goes from A to B in a chronological sense, but you know, it doesn't really mean anything about how it's resolving. So we don't use it. Instead of assigning a single function, you know, D picks out a single point in W, spits out a single semiote class in R. We can't do that, because as you saw with that previous poor example, it could be the same little 2-element thing could be multiple things dependent on what's going on around it. So instead, we can define a relation here. If you have some omega composition, you know the drill on that. You pick out a point in delta, which picks out a specific element of W. You put omega there because context is important, and omega includes parts of delta because that's just how functions work. And you include some class in R. This relation here is meant to relate these two with this one here, because you know these two are kind of a package deal. So by taking this little pair, we want to say this little relationship is true if and only if in delta, whatever our composition is, we have our x here, whatever x represents with whatever things, we want it to look the same up to a degree of change, mild degree of change here, as wanted to look the same and still work if we replace x with v here. All right, generic point of the semio class v, but if you can replace a point with a generic class representing that function and it still works the same, it would make sense to say that yes, whatever this point here is an instance of this generic class. But it might be true for more than one generic class. Like it might be true for V, for T, for and there's like 23 other letters of the alphabet. So rather than assigning a single definite function to our points, you instead assign, through a relational method, you instead assign a swath of functions in R here, which this point acts like in a loose sense. And the looseness can depend on just how far you're allowed to deform the thing. And as far as I'm aware, there is no canonical hard line for what should or should not be allowed for that deformation. You're just gonna have to pick a degree and stick with it. Because no matter what degree you pick with, you still end up with, although possibly different, a comparable theory of harmony anyway. So it's not an unimportant choice, but it's not important enough that you need to stress over it forever. Just kind of eyeball it. So now that you know it acts like anything in this patch of R, tells you a considerable amount of information, considering that D originally just picked out a single point, which may or may not even be in there. No, it's not may or may. It definitely is in there somewhere. In there, some nasty little spot. Of course, you know what you do with the fact that you've just carved out some part of R is yikes. But hey, now you can assign a context-rich function to any particular point. Use my pen. Let's see, what did I have written down after this? Oh yeah, nasty. So, you've got your weird little V thing. The question then becomes, how do you use these swaths to get functional harmony? A functional thing that's not things the transformational one. You know, how do you devise your entire theory from this? To which I say, still working on it. Considering I started working on this functional relational thing like a week ago. Whoops. So, you're not getting a whole lot of great answers on that one. Think on it yourself. So, sounds great and all. You've got Oh, cool, you got some fancy words. You got your semio classes, your derived transformational theories created from nesting it. But, like, does it matter? The answer to that is no, not really, because it's a very inefficient manner of working with things. The point's not to work efficiently with anything, is to work for everything, but work for everything inefficiently. Anyway, you know, there's no real concreteness to it. But let's say we made our W something more concrete. Let's make this a collection of all waveforms or something. And this one obviously has some extra structure, like you can amplify things, you can add stuff together, which is something different. Let's make R here. Why don't we make it something like, I don't know, a lattice ordered ring, maybe. Which is proper mathing. Anyway, in rings and partial orders and stuff do not necessarily have to be linear. You can have some horrifying branching things, but this lets you add stuff, this lets you multiply stuff, and we're going to have our function D go from R to specifically the positive part, or from W to the positive part of R. Negative stuff doesn't matter. We're ignoring it. It exists as a formal complement to things, but it is garbage. So, you have all this, so what does that matter? So, let's say you have whatever arbitrary thing. Your little composition in the of waveforms here. You assign it to your lattice order ring, which, by the way, the lattice ordering is important because you can do some like integration stuff on it, which is disgusting, by the way. So you've got it to your little lattice ordering, and it's all going to be in positive. And you also want to have some specific things like, oh, the empty maps to 0. Because you're going to have a waveform that's just silent. So just put it on 0. So R is going to look something like it's all going to be positive going up in whatever fashion. And there is a definite direction to it. So what if we just flatten it to a straight line? And one of the best straight lines that are a lattice ordered ring that everyone seems to like is the real numbers. Uh-oh. So, instead of dealing with some horrifying, nightmarish thing with branching and incompatibility to compare things together, just put it all in one straight line. And rather than caring so much about how does this relates to that, relates to this, relate to that, compare it in a linear fashion, which neglects a lot of structural stuff going on, like motivic recurrence, but by doing so, you basically just create a graph for tension and release, which is fairly helpful. And one thing you could do is anything here at the very bottom of whatever thing, maybe not the bottom of the whole thing overall, but the bottom of everything you're working with, you could consider that a sort of tonic, right? and we're going to call it the dual thing that's everything goes away from, downward from an antitonic. You know, like a diminished seventh. There's not a whole lot you can do worse than that. And in anything diatonic, you're probably just going to resolve down. So, you know, your tonic, your antitonics, whatever. As a nasty little habit of the fact that we started something at the bottom here at 0, and the fact that you're probably not going to play something for eternity, you're going to have a lowest point. And because it is totally linear, that point, you know, it's a straight line. So you just pick the lowest one, least value. Of course, it's going to be lower than everything. So that gives you a sort of tonicized area in very rough terms. So with that little tonicized area, if you pull it back to whatever you had, move it back to here, which this works even if your thing's not like waveforms or whatever. If you can put it into something totally linear, you can pull it back to a sort of up to, you can consider like putting it on a real number line, like a performance, a realization of it. Real, funny. You consider it a realization of it, and in that that effective tonicization of whatever point or points, it should align, because you know you're going to go down towards the tonic and then back up. So your local minima, you know, if you're, well, I suppose local minima might not be the best term, but as you're going along in delta, like whatever, here, you can now assign a single real value, like, oh, here's a 3, here's a 4, here's a 2. Oh, that 4, that's a maximal point. So that acts as a sort of local antitonic. A sort of a, what's the word? I forget the words, like in dynamics. It's like not a stationary point, but it's, you know, at that point it's stable, but it's, everything radiates away from it. Anyway, I can't remember the term for it. You get the idea. Everything wants to go away from it in our little local area. You know, it might go up or down a little bit here, so you get some in even localer areas, but in this whole area, this is the big bad, and since this is at the bottom, this is the local tonic of this subsection here. Which, as an aside, you're going to have a local tonic for the whole piece, because there's always going to be a lowest thing, but these local tonics here should, you know, you're going to have a highest point, you're going to end up with something roughly like, oh, exposition, you have a nice little climax. It's almost like one of those trashy graphs they show you in like junior high school English class about like literature progression. Of course, it's not necessarily unique for any given way to put it on the reels, but oh well, too bad. Even if it's not unique, you know, you don't necessarily need to be able to analyze a musical piece uniquely. You just analyze something with whatever tools, and whatever results you get out of it, you make justifications based on it. I mean, the whole point's not necessarily to have a single definite answer, but to have a language with which you can speak about multiple, whatever arbitrary number of possible answers, because, you know, music is a bit subjective after all. So what's important is not so much a specific analysis as much as it is that an analysis exists or can exist at all. Any questions? Which, while you're doing that, I'm going to see if I can pull up. No, I cannot, because I do not have it. I've been had. Downside, just got memed. Upside, I now know I no longer have that document on this laptop if I ever had it at all. Win-win. Because I had like a 1 or somewhere between 1 and 3 write-ups specifically on these cases where you have these partially ordered or otherwise lattice ordered rings and relation to realizations, which I guess I don't have on my laptop. Unfortunate. I mean, there were some nifty little things you could do. Like reopen this up because I ended up accidentally closing it. There were some nifty little things you could do, like if you, so long as you had some system with at least 2 distinct points, you know, an up and down, right? UD might conflict with our earlier uses of G, but shush. So long as you have these 2 things, and as I mentioned earlier, you're going to have your extrema, you know, it's going to be a point here, a dip there. Because if you know all the extrema, you know everything in between, because it's going to be a straight line. Or if not a straight line, a roughly straight line, which does not change direction. And for some of the relevant things you can do, like one variation that you can do, which would be something like this, d omega at t dt for a given arbitrary t0, which changes the values, specific values you get, but shouldn't change the extrema. So you pick out your, shouldn't change them significantly. You pick out your extreme points here, and this one's always going to be linear. It's just kind of a fact of it. So as long as you know these linear, these extrema bits, with just this up and this down, you can create something with an equivalent up bits and equivalent down bits. Though not necessarily equivalent up and down bits together in one. Though I think for the sake of the top and bottom bits of this function, I think you can get one that I'd have to pull up the documents written up. It's been like, I don't know, a couple years since I looked at the computer. For one of them, you should be able to completely just get the extrema on both directions in a single representative point. So in any system, as long as you have at least 2 points. And since one of them is going to be a 0, all you need is 1 non-zero point. And using that, you can, if you only care about the extrema and how they relate to each other, sure, you could do that. Of course, you know, you lose information about which extrema are higher than the others, but, you know, again, it's not that there's exactly one way you can speak about anything. The point's to have a language to facilitate speaking about the thing. Yeah, that's all I got here with me. No idea if I ever had the PDFs I'm looking for on the computer or not, but they sure ain't on this laptop now. Anyone who hasn't run off yet have any questions?
I didn't. I just arrived, and I'm not quite like sure of what the lecture is about yet, since.
Don't worry, I'm looking at the music general, and it doesn't seem like anyone knows, but it's fine. It's kind of what I expected. It doesn't help that I haven't slept in a long time, and I've only eaten a Pop-Tart and drank an orange Fanta in that time. Nope. Wait, last night I had pizza, but... Wait, yeah, I did. Okay, if that's indicative of anything.
But like, if it's not too much of a, if it's not too bothering, like, can you like give me a little rundown of what's the whole lecture about? Like, I'm just a little lost since I just arrived.
All right, so W, your basic symbols, they represent your atomic objects in a purely syntactical form. R is your space of semiclass. It's the space of like the semantic workings going on there. However, you only interact with them through a little function D, W to R. You pick out a single chord and you assign it to a single generic idealized context-free function. It's context-free, so you can't do a whole lot with it as is. Well, almost context-free. Anyway, you know, you can do some things like, oh, yeah, you have like a triangle here, and you turn it to a triangle with some arrow directions on all the lines. And you can draw arrows between these things so long as they keep the arrows in the same spot, whether or not they shuffle the directions. Or you can allow like different operations which are compatible in some way, shape, or form with. I've got like a couple of route-ups on this, which rotting away in a folder on my computer. Anyway,
in a musical example of that.
What?
Oh, sorry. Yeah. And a musical example of that would be like adding like tension a ninth away of every like chord tone, for example, or something like that.
So for R has arrows between the points, and your deltas here, which this is a triangle, not a delta. It just happens to also be in a triangular shape. Anyway, delta also has arrows, so what you care about is when those arrows align with each other. Specifically when they align, when the arrows on the R side, there's like a special class of admissible. It's an arbitrarily decided class, but it's important because it's admissible. It's the things we like. So you care about when the arrows are in the same direction as this admissible things, when they're in the opposite direction, and you know, when there's a directional arrow there at all, which is semiadmissibility. And whenever you have functions between your directionally challenged triangles here, if you want to go from this top one here, which is kind of in a cycle, to this thing here, which is not, to this one here, which is a not, you'd want... Mm-hmm. It doesn't matter that the arrows aren't in the same direction. It matters in their same shape. Not allowing rotations and stuff. So anyway, basic rundown of that is that W here, you map to points in R, and now you've got arrows between them. Take these as points. Now you've got your special class here, which is going to be your semi-admissible higher order transformations. Repeat ad infinitum. Congratulations, you just invented transformational music theory. or transformational music theory as interpreted by this area with unwritten admissibility class somewhere in here. There's another convention you could do where only important transformations exist, but there's a lot. Bleh. All right, so what was that? Any questions?
Can you show like a musical example of this being applied?
Well, I did have like one thing which I've written like a couple of write-ups, which have also just rotted away in the documents folder or on paper for notes. For W, take your waveforms, which also has like some added stuff you can add and subtract and stuff. For R, make it some ring, which I don't know if you know math, so that might not mean anything to you. It's going to look like the integers, except it might be, more branching-y and nightmarish. So what you do is you take your thing, your delta here, you got your composition, which picks out your points in W, and you take your D, and it puts it into some garbage here on this, right? But that's disgusting. You can't necessarily always compare things. The fact that it's lattice ordered means like no matter what your 2 points are, you can pick a closest approximation on the top and bottom, and you can kind of linearize it that way, with the ... Right? But that's disgusting. We don't like that. So what we can do anyway, let's just put it on a straight line, the real numbers. Tension on top, bottom 0, and release. Now you've got your whatever function. Top bits are the local extrema in whatever balance that they are extrema within, kind of act as antitonics or tonics. Tonics on the bottom, antitonics on top. Like a tonic acts like a tonic. Antitonics like a diminished seventh. Everything goes away from it. It resolves to everything within your area. You're going to have something that's the highest across the whole thing, lowest across the whole thing, and that's sort of... It might not act as a tonic for the whole thing, but it's the closest thing to a global tonic you're going to get. But, it might really be a tonic in this area. So this is a realization. You lose a significant amount of information, but if you have any, no matter how detailed this is, if you have another system with 2 points, you can get rough approximations. And furthermore, if you've got some real number stuff going from like the reals to delta, as well as from R to the reals, if you've got that, you can also do some nasty little integral thing, which integrates your whole thing from R to R over a little window. That's going to give you some peaks and stuff, and this will absolutely be straight and pseudo-linear due to some assumptions on the fact that it's waveforms. And as long as you have 2 points in the non-trivial, not only can you get a rough approximation in a positive half and a negative half, you should be able to get a rough approximation of this whole thing as far as extrema are concerned, but without amplitudes. It's just high and low.
I'm curious why you use the term like tonics and antitonics for like intensity values, since like we usually use like those terms for frequency variables, right?
Well, I mean, rather than thinking of a tonic as a specific
frequency related.
pitch, if I'm interpreting your question right, which
Yes.
I'm running on low.
Yes. Exactly. That's what I meant. Yeah,
rather than
because
thinking of a tonic as a specific pitch, you should instead think of it as a center around which the area around it, the tonal language is built around. It is the bottom. Everything is based on it. And the thing that makes it tonal is not that there's something just to be based upon, but that everything resolves around it, resolves to it. And in that sense, you can have tonic, quote unquote, in any abstracted transformational system or functional system, in the sense that it acts as a tonic in a similar abstracted sense, and the antitonic's just a dual notion, because you're going to have ups and downs, so you might as well just put something on the top if a top exists. You might not have an antitonic, but you will have a tonic.
I think I get it. So like we would get like release once we reach like certain intensity, and more tension once we have like the opposite like value of intensity, like if we apply the proper transformation to our like reasoning, right? No? Yes?
I mean, the point of the...
Like we shift our reasoning from frequency-based release intention to intensity or something like that?
Rather than thinking of it as a frequency-based tensioning thing, you should instead think of it as a... this generic point here is at the bottom. Rather than thinking, oh, it's just based on the frequency. We don't... In this interpretation here, I really don't care about what the symbols exactly mean. The point is, this is at the bottom. It is therefore a tonic. Everything resolves around it. Or revolves, but either one works. And in that sense, it's not so much a true tonic as it is a abstraction of it, but I mean, everything else is.
Cool. I got another question. So I'm not sure if you already mentioned like a book where you like read all this theory from or anything. But
so if you want some
is there any
for the stuff going on under the hood here, I've borrowed some terms which I've not read the book in its entirety, but it's probably not, entirely unrelated. Ever heard of Guerino Mazzola?
No.
All right, so that Topos of Music, specifically if you're going to look at like the second edition, Volume 1 Theory. Anyway, he's something, but if you're looking for like the transformational theory I approach, I was sitting in a Discord with Alexandre Popov, and then he's French, I can't pronounce it. I'm just going to type it out here. So you had Alexandre Popov here. So he had a similar thing with PK-nets, which is a specific categorical thing with Poly-Klumpenhauer networks. Anyway, point is, it looks looks relatively similar to my functional thing. You've got your delta here, whatever triangle of whatever shape. You map it to your thing, which is your objects, and you realize it as a result of some functor to set and a natural transformation between it. So I'm going to assume you're not going to know math. So this here gives a set.
Yeah, you can speak in math if you want to.
So I'll not be mixing up the direction of these two things. Anyway, so point is, this functor here from this generic shape here into your space of, really it's transformations.
Mhm.
So in the space of transformations, right? So like transpose up a third, down a fourth, whatever, for each of the arrows.
Mhm.
You also take this shape and you pick out points of the set, like let's say you have like a 12 tone little circle. You pick out some points for this starting chord, this F, you've got the transformations, you apply it, which is what's kind of going on here, and you end up with a specific chord there, right? But then you have transformations, with natural transformations where like the whole thing, so you know how this arrow is like between the functions, you got some category. So you'd have a different function here and a natural transformation between them to the same bowl here and here. But as you go around the thing, you can end up with like some sort of derived geometry of where things are related to each other on this fact. And I was sitting there in the group chat telling him about it, talking with him, and he's like, yeah. So it's not like I'm going completely off the deep end, misinterpreting what he said. Horribly, anyway. So the title of it, I'm not going to try and type it out because it's not going to be right, but it's like a categorical approach to Pauli-Klumpenhauer networks. Just look up his name. You should find it. As for the rest of it, not
I'm looking
for original.
Lip again.
Well, there's some ideas I'm using, like, functional stuff exists, but it's not like I'm just copying the research of someone else. If it's similar to someone else's thing, it's pretty much coincidence. Any other questions from the 3 people still here?
Right now I'm looking for books from the people you mentioned, the people you wrote down in the lecture chat.
Doesn't
so
do books. He does articles, and his stuff is just straight up math. Like there's not there's a hint of music theory behind it, but nah, it's basically I'm not gonna say it's bad because it's well done, but it's not purely interesting mathematically.
It's more about
the music
systems
stuff
than
is
music.
kind of half done, so it's good as mathematical music.
I mean,
but
it's cool.
Not good as either specific one. And Matt Sola's is just a wild ride, and I don't like reading it.
Cool. I mean, I'm interested because a couple of years ago I studied acoustic engineering, so I got a little background in math, right? I used to do some programming to apply numerical analysis in buildings, and I was trying to do some things in math lab, but I left it, and I started studying musical composition later. I abandoned the career, really. But I don't know, it might be a good chance to connect the dots between my musical background and my engineering background.
I will say right now, my thing is not for that, since obviously it's not designed around being computational.
No, yeah, but maths, around maths and music. Like I like both fields. So yeah, thanks so much. If that was the end of the lecture.
Nope, unless anyone else has a question. Well, they did stick around to ask it. Too bad, I guess. I guess if someone watches the video for some unknown reason.